In tensor analysis, now we are going to discuss a very important concept, and this is actually the concept of metric tensor or fundamental tensor. In fact, this metric tensor is a very important parameter to discuss the general theory of relativity. When you will study general relativity, you will always find that for a space we define a metric tensor and then we discuss any theory. So this metric tensor finds its application mostly in describing the theory which we study in general relativity. But in this basic lecture on this metric tensor, we will see the basic definition of this metric tensor, and then we will analyze this metric tensor in different coordinate system. So first of all, we have to know what does this metric tensor or simply the metric means. In fact, a metric or a line element, this metric is also known as line element, is defined as the distance between two adjacent points. So you can say that an expression which expresses the distance between two adjacent points is called a metric, or it is also known as line element. In fact, if you consider a three-dimensional space, and you know the three-dimensional space is also known as Euclidean space. And in that three-dimensional Euclidean space, if you consider two adjacent points, let us consider first point is P having the space coordinate x, y, z as you can see here. And the another point is Q and its coordinates are x plus dx, y plus dy and z plus dz. In this condition, in Cartesian coordinate, we define the line element or the metric by the arc length ds in this way. You can say ds square equal to dx square plus dy square plus dz square. Actually, this ds is the arc length or the line element, or simply we say this is the metric in Cartesian coordinate. Now, in generalized curvilinear coordinate system, which I have discussed earlier in the course on mathematical physics, you will find my video on curvilinear coordinates, and in the introductory lecture on curvilinear coordinates, you will find the definition of the line element or the metric in terms of generalized curvilinear coordinates. If you cannot remember, definitely you should watch my video on the curvilinear coordinates, and there you will definitely find the concept of this metric. In fact, in terms of the generalized curvilinear coordinates, if you want to define the metric, the definition is like this. This is ds square equal to summation over I 1 to 3 summation over j 1 to 3 gij dui times duj. As you know, according to Einstein's summation convention, there is no need to write this sign of summation here. Without writing the sign of summation, we can write this, because according to summation convention, the summation is already implied for the repeated index. So this expression may be written without writing this sign of summation, which I have mentioned here. Now, this idea of metric, which I have just defined in case of the three-dimensional Euclidean space and in generalized curvilinear coordinate system, now we will generalize this definition. In fact, the generalization of the idea of metric is due to The great mathematician Riemann, in fact, Riemann generalized this idea of metric to the n-dimensional space, where n is not limited to 3 or 4. It may have any value. So, when we generalize the form of the element of length, that is arc length or the interval ds, between two coordinate points, then how we will define this metric element? This is due to Riemann. So we will follow exactly the expression which was devised by Riemann to define this metric. So the you can say the generalized form of the element of length which we denote by the symbol ds between two coordinate points, let us say xi and xi plus dxi as defined by Riemann. This is just the definition given by Riemann, a great mathematician, is given by the following quadratic differential form. In fact, this is nothing. This is just the generalization of the definition which we have just seen in case of the Euclidean space and in case of the generalized coordinates. So this definition is like this: ds square equal to summation over I 1 to n summation over j 1 to n gij dxj, and using the summation convention devised by Einstein, you can also write this expression without writing this sign of summation. You know, this may be written as simply gij dxi super I dx super j. This is in fact the definition of the line element or the metric. In fact, here I have used the summation convention. So you can say using summation convention. In fact, in this equation, the coefficient gij, these are functions of the coordinates xi. Here, the coefficients Gij are the functions of coordinates xi. In fact, here in writing the values of Gij, we have assumed the following facts. First one is, you can say that this Gij are functions of xi, as I have mentioned just now, and the another fact regarding this is that this Gij is actually symmetric. It means Gij is equal to Gji. So you can say this coefficient is symmetric. This is symmetric. And another important fact regarding this is that the determinant of this coefficient Gij is not equal to 0. So the determinant of Gij is not equal to 0. In fact, in this condition, when these properties are satisfied by Gij, then the space is known as Riemannian space, and the quadratic form which you have defined here in this equation 1, this is known as actually metric, or you can also say metric tensor or fundamental tensor. So in this condition, in this case, you can say in this case the space is the space is called, which space? This is called a Riemannian space. Riemannian space. Riemannian space. And the quadratic form defined in equation 1, that is known as the metric or metric tensor. And the quadratic form you have seen, this is Gij dxi dxj is called metric or metric tensor, or you also call it a fundamental tensor or fundamental tensor. So you have to remember this basic definition of metric tensor given by Riemann. In fact, as I have told you earlier, that the quadratic differential form which I have mentioned here, this is actually independent of the coordinate system, and this is known as Riemannian metric for the n-dimensional space. And the space which is characterized by the Riemannian metric is known as Riemannian space. In fact, here the quantities Gij are the components of a covariant symmetric tensor of rank 2, As you can see, this is a covariant tensor of rank 2, and it is, you can see, it is a symmetric tensor. Now we will see some of the special cases to define this symmetric. So first of all, let us see as an special case when the metric is defined in an n-dimensional space in a particular manner, which I am just mentioning here, then you call that the metric is defined in the n-dimensional Euclidean space. So if the metric is represented by like this: dx1 square plus dx2 square plus dx3 square plus so on plus dxn square. Or you can simply say this as dxi dxj. If you define the metric in this manner, then actually the space is called n-dimensional Euclidean space. Then the space is called n-dimensional Euclidean space. N-dimensional Euclidean space. N-dimensional Euclidean space. In fact, it is obvious that Euclidean spaces are the particular cases of the Riemannian space, as you can see here. Now, in general theory of relativity, as I have told you, that in case of general theory of relativity, this concept of metric is invariably used. So we will see how this metric is defined in case of the general theory of relativity. You know, in general relativity, we consider that our space is four-dimensional. So if you want to define this metric tensor in case of the four-dimensional space, which we assume in general theory of relativity, then how it will be defined, you will see the definition is same, only the number of coordinates of a point will be 4, limited, that is limited to 4, not in general n. So you can say in general relativity, or in G, I am writing here in short GR, this is general relativity. That is, when you say general relativity, it means you are considering the four-dimensional space. Four-dimensional space. The metric is given by. In fact, in this case, we define this ds square equal to gij dxi dxj. But here, I and j assume the values 1, 2, 3 and 4. 1, 2, 3 and 4. But in case of special relativity, we also consider the 4-dimensional space, but in this case the 4th dimension is in fact imaginary, that is ICT. So you can say in spatial relativity, SR for spatial relativity, the metric is given by, this is defined like this: ds square equal to dx1 square plus dx2 square plus dx3 square plus dx4 square. And you know here in fact the 4th coordinate x4 is equal to ICT, where I is for imaginary, that is this is a square root of -1. And in brief you can write this expression as this is dxi dxj, and here actually sorry not j but dxi and dxi, not dxj. This is also I, dxi, and this is this I is equal to 1, 2, 3 and 4. 1, 2, 3 and 4. So this is the different form of the metric tensor in different cases. So first of all, you have seen its definition in case of the 3-dimensional Euclidean space. Then you have seen this the definition of this metric in terms of the generalized curvilinear coordinate system. And finally, we have seen the definition of this metric tensor given by Riemann in the Riemannian space, that is n-dimensional space. Now you have seen just now that this metric is defined in general space, that is the Riemannian space, and it is independent of the coordinate system. Since it is independent of coordinate system, so this metric is actually an invariant. So you can say this is a very remarkable fact, as ds square equal to gij dxi dxj is defined in general space. General space, it means we define it in Riemannian. When you say general space, that means Riemannian space, that is a Riemannian space. A Riemannian space. So it is independent of the coordinate system. Independent of the coordinate system. And so you can say that this ds square equal to Gij dxi dxj equal to an invariant. It means due to the change in coordinate system, this metric tensor does not change. So this is just an invariant. So in this short lecture, I have just introduced you the metric tensor, but we will discuss in detail this metric tensor in the forthcoming lectures separately. And so remember this definition, and you will find the detailed analysis of this metric tensor and its application in my forthcoming lectures.